IPv6 tools from the hacker's choice. These are some of my favorites. Let's begin. I'd like you to imagine that you and I have decided, this IPv6 stuff is catching on, and we would like to go ahead and focus our energies on pen testing for IPv6. Well, in a previous nugget, the one titled Parasite 6, we discovered how easy it is to go ahead and do a man-in-the-middle attack with IPv6. Now, the same folks who brought us Parasite 6 have a whole boatload of additional tools for both IP version 4 and IP version 6. THC stands for the hacker's choice. And what I'd like to do in this nugget is highlight a few of my favorite IPv6 tools from this group and demonstrate them for you. So let's discuss these, and then we'll demonstrate them in that order. So rogue IPv6 router advertisements. When a router comes up on the network, if it's able to do IPv6 routing, it's so proud of that, it advertises that information. Also, a client coming up on the network is going to do a router solicitation, which will invoke a router advertisement so it can learn things like what network am I connected to, and who's a good candidate for a default router, and so forth. Well, as a rogue device, we can go ahead and generate these. In fact, we can not only generate router advertisements, we can make ours have preference over the default router advertisements that are being sent by R1. Effectively, we could have everybody believe that we should be their default gateway, and they can be on any IPv6 network that we tell them that they're connected to. One of the challenges we have with our IPv6 tools is that if we have a subnet that can support trillions of possible addresses, which they can, we have 2 to the power of 64 possibilities for scanning, we're not going to be scanning entire subnets like we did with IP version 4. So how do we know exactly where devices are? Well, there are some tricks we can do. For example, we could ping to the all nodes multicast group. That would get a response from many. And we can also just run a tool that will listen for new devices as they come up on the network. So we leave this tool running, and as new devices come up, it simply displays what those IPv6 addresses are, both the link local and any global addresses that those devices are going to be using. When a new IPv6 device comes up on the network, it wants to make sure that the interface ID, sometimes referred to as the host ID, that last 64 bits, it wants to make sure no one else is using that exact same address. So it actually sends a neighbor solicitation to the solicited node multicast group address of anybody who would have that address. And if it doesn't get a response, it says, okay, that address is free, I'll go ahead and use it. Well, what if we train this BackTrack system to this is so mean, to listen to every single neighbor solicitation and then reply saying, oh yeah, that's in use. If we did that on the BackTrack/Kali system, we would prevent many, many devices from being able to even get an IPv6 address that they can use on the network. It's a terrific denial of service attack. Another really mean trick that we can do is router advertisement flooding. So our BackTrack/Kali device simply pumps out tens of thousands of bogus router advertisements, and all the devices on the network say, oh, there's a router, there's a router. They're going to keep track of that in a table. It's going to tie up CPU, it's going to tie up memory, and potentially cause a denial of service on devices that can't handle that. Another really mean trick, in addition to router advertisement flooding, is neighbor advertisement flooding. IPv6 cares. It's going to remember in its neighbor adjacencies who its IPv6 neighbors are, the layer 3, layer 2 mapping. Well, what if we send a few 100,000 of these into the network and we have everybody try to remember that? That's also going to cause some damage and some slowdown to many devices on our IPv6 networks. Another really amazing tool is an implementation checker that we can launch against a router or another IPv6 host. And this can save us a boatload of time. If we're curious, I wonder how this device handles, for example, certain types of IPv6 header options. Does it handle RH0? Does it allow that? Does it allow source routing, etc., etc.? It'll send off all these packets, it'll get responses back, and then from the list of what it gives you, it will tell you pass or fail whether or not those features or functions have been implemented on that device. Another one that I really enjoy is the IPv6 Smurf. It goes something like this. The router is at 2001::1. This BackTrack/Kali box is at some other address on that same network. We send out a ping packet. We send it to FF02::1, which is the all nodes multicast group. That means basically everybody on this subnet is going to get that message. And we spoof it and we say the source address is 2001::1. So the ping goes out to everybody on the network, and those that do reply to this are going to go ahead and reply back to the router. It's kind of like a double whammy. And that's the basic concept with the Smurf attack. We have multiple sets of victims. So let's start with a baseline of what we have on this Windows 8 box. We're going to run ipconfig just to verify its IP addresses. And sure enough, the network of 2001 corresponds with the default gateways network. And that's because we learned it from the router advertisements from Mr. R1. And our default gateway is the link local address of R1. That looks absolutely fantastic. Let's go ahead and we'll train Kali now to go ahead and start advertising router advertisements. So let's go ahead and run this. On the Kali box, the command is fake_router6. You specify the Ethernet interface that you're using. In our case, it's Ethernet 0, and then what you want the network to be. So right here, I simply said, yep, this is network 2001 DB8 bad, and this packet, again, the router advertisement is going to have a preferred status, and that's how they crafted this attack. So let's go back to our client and take a look at the difference. We'll go back to our Windows 8 box. And on our Windows 8 box, just for grins, to give this guy a fair shake, I'm going to go back to the control panel, and I'm going to disable this interface for a moment and re-enable it. Now, when I re-enable it, what's going to happen is we're going to have router solicitations, and those are going to be seen by R1 and also our Kali box. They are both going to respond. So we take a look at the end result of that. If we do a clear screen real quick, and then issue that same command again, ipconfig, check this out. So now it has two global addresses right here. One for the 2001::, network, one for the 2001 DB8 bad network. It also has some temporary addresses used for privacy extensions. And then it has a link local address. And check this out. As far as its default gateway, it sees a couple. It sees the FE80, 200, yada, yada, yada. See those 7s in there? Those 7s represent an EUI64 address based on the MAC address, and also FE80::1. So it has two default gateways. Now, which one is it going to use? To find that out, we can ask the device to show us its routing table on Windows 8, or we can use the netsh command for that. So this command, netsh interface IPv6 show route, will show us the routing table from this PC's perspective about what it's going to do. Now, this is the fun part. It's got two default routes for IPv6, these two right here. One has a metric of 256, one has a metric of 16. With metrics, lower is better. And the one with 16 points to this bogus, was our BackTrack/Kali box that where we just launched the attack. And the other one points to R1. So not only have we tricked the device into believing it's on a completely different and wrong network, we've also told it that, hey, we are the Kali box, the default gateway that you should be using to move packets to any remote networks. So on our Kali box, if we're doing IP forwarding, we can go ahead and continue to forward those packets on behalf of that customer. Or we can just cause a denial of service attack, because any packets trying to leave the local network would be forwarded to the Kali box, and if we're not forwarding, that's the end of that packet. So I'm going to stop that attack from happening with a Control-C, and that'll allow the network to settle down back to normal after a short period of time. One of the security benefits of IPv6 is that because the IP subnets are just so darn huge, it's not very likely we're going to do a ping sweep or a port scan across the entire range. It would simply take too long. So how do we find out exactly which devices are on the network? Well, there's a few methods. One of them is a tool from the THC group, and that is Detect New IPv6. It pays attention to the duplicate address detection process, and it simply reports any new devices that it sees. It's simple to launch with detect-new-IP6 space, the interface that we're going to use to listen on, and then let's go ahead and trigger a device coming on the network. This is our Windows 8 box again. We're going to simply disable the interface and then go ahead and re-enable it, and that will allow the duplicate address detection to happen, and now we know exactly what IPv6 addresses are in use. So here's the link local address used by that guy, and then there's two global addresses, one for reaching that device and the other for the privacy extensions portions of IPv6 as implemented by Microsoft on this Windows 8 box. So that's a fantastic way to quickly identify new devices that are popping up onto the network. So I'm going to stop this attack with a Control-C, so we're no longer listening, but we could certainly leave that in a window. For example, let's say we had Kali running on a little Raspberry Pi plugged away somewhere, and that information was listening 24/7. No problem. We can just gather that information and use it at our will when we needed to. Another thing we can do is we can go ahead and say, you know what? I don't think any new IPv6 addresses should come up on the network. This is not nice, but here's how to do it. Basically, duplicate address detection is a client saying, hey, I wonder if this interface ID, the last 64 bits, is in use. They send out a message to the solicited node multicast group for which they believe that device would have joined, and they wait for a response. Well, what if we did something like this? On this Kali box, If we say DOS new IP6 with the hyphens in there, and then specify the interface that we want to use. So here's the command right here. This is so mean. This device, this Kali box, every time it sees a duplicate address detection message come out, it'll reply saying, oh yeah, that's in use. Oh yeah, that's in use. Oh yeah, that's in use. And as a result, we can prevent a client who would normally get an IPv6 address from ever using one because he thinks that they're all in use. And after a period of time, they're going to give up. So with this attack running, let's go ahead back to our client over here. And I'm going to bring down this interface one more time. He doesn't mind. And I'm going to go ahead and bring it back up with enable. And as it comes up, you'll notice that he's now doing spoof packets. And this would imply right here that the Windows 8 box asked 1, 2, 3, 4, 5 different requests. So 3 of those were link local addresses, and 2 of those were for global addresses. And unfortunately, this Kali box said, oh, I'm so sorry. Those are all in use. So what's the Windows 8 box going to do? I don't know. Let's go take a look at it. Let's go back to a command line and simply do an ipconfig and say, what are you going to do? So it looks like it got a link local address, which is pretty cool, ending in 26BD, but it did not get a global address. So it's not going to be talking on the network very effectively as an IPv6 device with only a link local address. Let's go take a look at 26BD and see if that's in this list as well. So right here, check this out. It actually sent back a message. Perhaps it didn't send it back fast enough because if we spoofed a packet saying, oh yeah, that's in use, that should have caused the Windows 8 box not to use it. So we could experiment with that and say, oh, maybe that's a timing issue. It didn't get the response back fast enough based on this box, etc. But that's the process. That computer, that Windows 8 box is not going to be happy without a global address that it can go ahead and use. Now, to demonstrate this, we could stop the attack, do a Control-C once again. Now the attack's not running. I'm just going to do an up arrow key real quick, ipconfig, just to verify that he didn't magically somehow get a global address, which he did not. And let's go ahead and bounce the interface one more time. So we'll right-click, disable, and then go back and enable it. And let's go take a look again. So I'll do an ipconfig one more time, and sure enough, now he's got no problem. He's got his global address, his privacy extension global address, and he has his link local address. He is good to go. All right, so here's another mean one that we can do to the network. Now, when we spoofed a single router advertisement from this Kali box, the devices, they grabbed a global address from both networks they were connected to. So 2001, they had an address, and then 2001, DB8, I think it was 67. Oh, it was bad, was the address that we gave it. So grab one from both. So what would happen if we pumped, I don't know, a few 100,000 router advertisements spoofing all of the source link local addresses into the network? What would happen? Well, each device on the network based on Windows 8 or other Linux boxes or Macintosh or Windows XP, they would handle it the best they could, but they're going to try to remember all that detail about all these additional routers that it thinks it sees because of the all unique router advertisements that are coming in. It's going to cause a bunch of pain on virtually every device in the network. So let's go ahead and do that right now. We'll go back to the Kali box, and on the Kali box, we're going to type in flood_router6 space and the interface that we want to do it on. And it says that every dot that's printed represents 100 packets being pumped into the network, all with these router advertisements. So let's do this. Let's go ahead and bring up, I have all this set up inside of a virtual environment right here. If you are a subscriber, which I think you are, so with your subscription to CBT Nuggets, you've also got a subscription to my GNS3 series. If you want to lab this up in a private environment, not damaging anyone, GNS3 is a great way to do it. And my GNS3 series walks you through the entire gamut of how to get it up and running and working in very, very creative ways. So in the cloud, I've got BackTrack, and I've also got the Windows 8 machine, and I've also got an XP box hanging out in there. And this is gig 1/0, and the IPv6 address of R1's interface is 2001:1/64. I also hard-coded the link local address as FE80::1. So what I'd like to do is let's go ahead and let's eavesdrop right here on this interface. And we can do that by right-clicking and click on Start Capture. And then I'm going to say, yeah, I want to see that. So we'll do a capture, and then we'll take a look at the output. So what's happening is, and I'm going to pause the screen just for a moment so we can look at this. It's just pumping out router advertisements like crazy. And take a look at the source addresses. They are all over the board. So just since we started that capture a few seconds ago, that was 1,300 packets. And if I unpause the screen here, we're at 6,000. and close to 7,000. So it's pumping them out as fast as it possibly can, and that's really messing up the clients on this network. So I'm going to stop this capture just for a moment. I'm going to stop it here. I'm also going to go into GNS3 and stop it here because I don't want that running indefinitely in the background. I'm going to minimize that, and let's go back to our client. Now, just a few moments ago, we did ipconfig. I'm going to hit the up arrow key. Check this out. When we hit ipconfig, and as it scrolls through, look at all the IP addresses this poor computer is trying to get for itself. So global addresses, the temporary addresses, and now we're at the default gateway portion. So if we scroll up, I almost feel bad for it. So these are all the default gateways based on the router advertisement. So there's some limit, otherwise, because we're sending thousands and thousands into the network. So these are all the default gateways that it's putting in for IPv6 based on all the spoofed RAs. Here's a whole bunch of temporary addresses based on the first 64 bits. 1, 2, 3, 4. That's this section over here. And if we go higher, we'll have the addresses right here. And again, it's trying to do one for every single network that it's connected to. And again, there must be some limit based on this operating system that would, tell it, okay, it's time to stop, or first in, first out, or something else. Let's go take a look at another victim. Let's go take a look at an XP box, for example, and see what he says. So on this Windows XP box, let's go ahead and, oh my gosh, check it out. I can't even move. Now, I cannot move the windows here. Probably the CPU on this or something is too messed up for it to even. Let me stop the attack real quick. So Control C to stop the attack. Give everybody a breath of fresh air. We'll go back to the Windows XP box, and now in Windows XP, no, I still can't move it. He may be toast. He may not just have had the energy to handle all that, and he went belly up. So depending on the operating system and how they handle it, maybe with XP and the implementation of IP6, maybe it simply didn't have a limit and it tried to put all of them in there, and as a result it is no longer functioning. Now this is a virtual machine, so no permanent damage done. I can just shut it down, bring it back up, or I can bring it back to a snapshot I had, and I'll be ready to go again. Another thing that we could look at based on that attack that just happened is how did the router handle it? And let's see how the router... Oh my gosh, my router didn't handle that either. So that was a Cisco router in that GNS3 environment right here that I was connected to, and he's down. He is no longer functioning. I mean, GNS3 says, oh yeah, he's fine, he's good, but he is no longer running. So based on that attack that I sent with those router advertisements, for whatever reason he couldn't handle it, he is no longer functioning. To start him again, I could right click, I could say stop, and then restart him, and I could get him back up and going, which is effectively having to reboot that router to bring it back up. So I have rebooted R1 inside of GNS3, and there we go. So he's back up and happy. And it actually could have been several of the previous attacks that router just couldn't deal with that caused him to have grief. But certainly he was dead to the world, not even responding at the console port. So for things like that, if you want to test it, which I strongly recommend, you could launch an attack like this. Let's get a baseline first. Go back to your router. Again, in a test environment, let's do a show, process, CPU sorted. And you'll notice up here at the top, so because he just booted up, he's at like 10% utilization. So on R1, if we wanted to find out what really caused him grief, we can do a show, process, CPU, and so we have a process of about 8% right now, which might be average for a various network, and he's got some NAT and some other things going on that he's doing at the moment. So let's say the baseline is 8%. In fact, let's do one more little test. I'm going to hit Q, and I'm going to do that command one more time. So 8%, 9%, no problem. So let's go ahead and launch that same attack and see if that's the one that really gave him grief. So we'll do a flood router 6 Ethernet 0. And again, every dot represents 100 packets. Let's go back to the router. So he's complaining about some hop count setting in neighbor discovery. That's no problem. Let's go ahead and do a show process CPU. Yeah, look at it climbing right here. So right now it says 56, and it's just going to go up from there. So let's go ahead and do it one more time. Now it's 72. Yeah. So it probably just got to a point where it got to close to 100%, and he had nowhere else to turn, to poor little router, and it simply went belly up. Or at least it wasn't responding to any commands at the console port, which is currently where I'm connected. So this little asterisk right here represents where I'm currently connected, and logically, in this GNS3 environment, I'm connected directly to the console. So it doesn't even need IP connectivity to talk to me. It just has to be willing to respond on a console port, which it wasn't. So if we do that one more time, show process CPU. Yeah, so it's 91%. And so it's very likely this attack that left running for quite a while is what caused this router to go belly up. Now, in saying that, I realize I should probably avoid doing that again. So I'm going to do a Control-C now, stop it, and hopefully the router will continue to respond to me, which it is at the moment. That's fantastic. Another attack that we could launch is very similar to the flooding of router advertisements. It's flooding neighbor advertisements. Because IPv6 keeps track of the layer 3, layer 2 mappings of neighbors it knows about, if we did the same kind of a technique, but instead of router advertisements, we flooded neighbor advertisements, it could also disrupt the network. So the syntax for that is very similar to the previous. It's flood. In this case, it's advertise 6, and the interface we want to send it on, and it's pumping these out like crazy as well too. So this is bothering all the devices on this subnet of 2001://64 because everybody has to process these. I'm going to go ahead and stop that with a Control-C. Another really great tool that will help us to identify how IPv6 was implemented specifically on a host is to run a tool called implementation 6. Now this is also from the THC group, and the syntax is implementation 6, the name of the interface you want to use, and then the target you want to send this to. So what's happening right now, 2001:1 is the IPv6 global address of our default gateway, and we're simply sending a whole bunch of different packets. We know it's handling fragmentation. We know that it supports source routing, and because basically the response that we got back. So this is going to go through like 50 plus different types of scenarios asking the router, not formally saying, hey, do you support this? But by sending it packets, and based on how those packets were replied to, it makes deductions that, okay, they're supporting this feature, they're not supporting that feature. And this can benefit us how? It's when we're trying to determine what features or functions we might be trying to leverage, take advantage of, or compromise on a device. Of course, all within a test environment where you have authorization to do so. And at test 54, it's doing a ping, and we might say, well, why is it doing a ping again? It did a ping way at the beginning. Why is it doing a ping at the end? It's possible that some intrusion prevention or detection system saw our traffic, considered it to be a little bit too much, and stopped allowing that packet or those packets through. So doing a ping at the end just helps us verify some of the results in that we didn't have an intermediate or that device itself filtering all future packets based on some point in our questioning. For the Smurf attack, all we're going to do is we're going to spoof who the attack is coming from. For example, if we say Smurf6, that's the name of the command, and then put in the interface we want to use, in our case it's going to be Ethernet 0, and then we say we want to spoof 2001:1, these packets are actually being sent to the multicast all nodes group, FF02:1, which means everybody gets a copy of this ping request. However, the source address is 2001:1, which is the routers. So individuals who reply to this traffic, they're going to be replying back to the router who's going to say, I never asked for this. And it's simply a great way to eat up a lot of bandwidth and tie up a lot of resources. So what might be fun here as well is let's open up GNS3 again, and let's just put a packet tracer right here. Now you could also simply open up Wireshark in another window right on BackTrack or Kali and look at it from there. But that's also going to, if you're remotely connected to that Kali box, that'll also show you the SSH and all the other traffic that's going along as well. Doing it this way in a test environment gives you a nice clean option of looking at just the traffic on a given segment of your network. So I'm going to right click, say start capturing, click OK. So I'm going to go ahead and stop that. And I'm also going to go back to GNS3 and say, please stop the capturing right there. So it's not capturing the background anymore. And if you look at the content here, so it says it was sourced, this ping, from 2001:1. That's not really true. If you look at the layer 2 address, the layer 2 address of the source is 0000 dead beef. That was the writer of this tool being very creative with which source MAC address he wanted to use. But that is that's actually coming from the Kali box that's sending this attack. The destination address is the FF02:1, which is the multicast all nodes group. And let's see if anybody's responding to this. So if we have any takers, they would be responding to this. Look at this. I've got nobody responding back to it. Now that's healthy because in a good network environment, if we get an ICMP message that's sent to the all nodes multicast group, we should not reply to it. However, some devices aren't quite that smart. And to demonstrate that, let me go ahead and close this capture for a moment. And let's go back to a Windows XP box, which I think is, he was totally owned. That's why he didn't respond. I'm going to simply refresh this box. I'm going to say, go ahead and power off the machine. It's toast. and I'm relaunching that box inside of VirtualBox. That's my virtual environment I use quite a bit for building networks and putting devices all next to each other. So because he couldn't respond, that's why he wasn't. However, the protocol stack implementation on different platforms isn't the same. So Windows 8 versus Linux versus Windows XP, you might have some devices that do reply, which they shouldn't, to a ping request that was destined to the all nodes multicast group, and you have other devices like Windows 8 that shouldn't. But I want to go ahead and verify that's the case. So this Windows XP box is booting up. I'm going to go ahead and let him do that. Let me minimize him for a moment. And let's launch this attack again. Oh, actually, the attack was running. So let's give that Windows XP box just a moment to come up. Then we'll launch the attack again and see whether or not he is going to respond. So I'm going to go back up to my GNS3, right-click here, say Start Capturing. Stop the capture here as well. And here's what I was looking for. This is the actual IP address of our Windows XP box. So if we bring up Windows XP and we go to command prompt and do ipconfig and we look at the last digits here. So the last digits are B40B, and if we look at our trace, that is exactly the last 4 digits that is replying. So what happened was the XP box got this request right here. So it got this request, ICMP ping from 2001:1, which is spoofed from our Kali box, going to the all nodes multicast group, and the XP box said, okay, I need to reply, and it replied back. So it replied from itself to the global address of the router, who then got that packet and said, I didn't ask for this. It wasn't useful, but we're chewing up bandwidth and we're chewing up resources on that router because it has to deal with every single packet that comes in, says, do I need this? Is it for me? Is it applicable? No. Discard it, on to the next packet. So if we leave this attack running just for fun, which it is at the moment, let's go ahead and let's just do a show process CPU. And look at that. We are totally chewing up the CPU resources on this router. And that's primarily because it has to go ahead and address every single one of those ICMP messages that's going to its IP address. And most of this is courtesy of our good friend Mr. Windows XP, who is replying over and over and over again to all those ICMP requests. See, 1 or 2 bad clients, or maybe not well implemented clients, can have a negative effect on the entire subnet. In this video, we've taken a look at some of my favorite tools in the world of IPv6 from THC. I would strongly encourage you to practice with them in a test environment where you're not going to destroy anything. See, in this demonstration, I had not intended to blow out the router. I had not intended to lock up the XP box, but both of those things happened by simply running these commands. If that happened on a production network at your hands, that would be very, very bad news. So I've supplied for you in the Nugget Lab download area the actual commands that I've used in this video. So if you want to replicate those again in a test environment, you can do so. I'd also strongly encourage you, if you're brand new to IPv6, go and check out the IPv6 Nugget series on IPv6. It's fantastic. I think you'll love it. I also have the GNS3 inside of CBT Nuggets as well. So take advantage of all those resources with your subscription. I've had a great time. I appreciate the time you spent with me. I hope this has been informative for you, and I'd like to thank you for viewing.